Dear colleagues, this is my pleasure and great honor to open the today's conference, which is the 20th conference of the doctoral school, and at the same time, this is the fourth György Oláh conference. Since the establishment of our doctoral school, yearly we organized a forum for the young scientists to present their work, and that's why this is the 20th occasion for that forum. And 4 years ago, we decided to extend and a bit further develop that conference, and we established the György Oláh conference. And the major change was to change the language of the conference from Hungarian to English. This is due to the idea to give the opportunity to the more and more foreign students doing PhD work in our doctoral school to be present in that conference as well. And it gives a bit more international feeling for our students as well, because usually the language of the international forums is English. And the first György Oláh conference 4 years ago was really a success story. We had a lecturer from Canada, a well-known scientist, and since this year, since that year, yearly we could invite various international lecturers. Today, we also have Professor Hans-Jörg Günzmacher from Germany, who will present the last lecture during the morning session. And we also decided to give a privileged opportunity to our industrial partners. Every year, one major partner of the doctoral school presents the results of their area and the possibilities of that industrial company. This year, Furukawa Institute will provide us with a lecture on their research area. And this is the possibility again to make the conference as a real conference, being present physically in a room, because the last two conferences were organized online, although it was a great success as well, because many young scientists could present their results in the last two conferences. But due to COVID, that online conference era is not the same as the real conference. And this year, we could organize again the conference as a real living occasion. And this is the year when we also extend the conference, and we decided to give the opportunity to the partner doctoral schools related to our area of chemistry and biotechnological research. And we invited several of the Hungarian doctoral schools from the related area. And this is the reason why the linear setup is not useful anymore, because we had really a large number of interests. More than 1/4 of the lectures are from partner doctoral schools, and that's why at the afternoon session we should organize 2 parallel sessions. And I think this conference will give you the opportunity to provide us with your nice results. We needed to select, so we could not give the opportunity to all possible speakers. We sent several of them to the poster session due to the time restrictions, but it at the same time give us some quality insurance, so really the best lectures will be provided. And I think all the results which the young scientists will present us will show that you are enthusiastic, you are talented, and you will be able to solve the future challenges of climate change, something like COVID. So we're really proud of you, and we hope that you can continue your nice career in the future. So thank you so much, and with that words, I declare that conference is open. And at the same time, I will donate to myself the chairmanship because at the same time I will be the chair of the first session. And it's also a historical habit on that conference is that the yearly Oláh prize winner of the doctoral school presents the first lecture. So this is the most prestigious first lecture. And this year, this lecture will be presented by Brigitta Nagy, dealing with mathematical modeling of chemical process technology for pharmaceutical production. So I would like to ask Brigitta to present us that lecture. And before that, I will give you the document for the Oláh Prize winning. And congratulations.
Thank you very much. Well, I'm Brigitta Nagy, and in this talk, I would like to talk about the mathematical model development and the quality assurance of pharmaceuticals. I would like to show mostly some examples. So the first question is why we should care about modeling at the first place. So as you all know, in the pharmaceutical industry, the quality is the most important because when we are sick and we have to take a medicine, we want to be sure that it's safe and it's also effective. So the pharmaceutical companies make this work by using approach which is called release testing. And this is done for each production batch. And this is a series of testing, starting from the checking of the raw material and also the analytics of the final products, such as content uniformity, dissolution, stability, purity, and so on. And it also means a series of documentation too. Unfortunately, these processes are quite expensive and time-consuming, and also labor-intensive, so it's not very ideal. And because it's an end product testing, it also means that we can't make any preventive measures when we detect a problem, so the product has to go to waste. And also the documentation also hinders the development sometimes. So luckily the pharmaceutical industry and the regulators has realized this. And there are some new emerging trends today that aims to tackle this problem. So from the technological perspective, the use of continuous technologies is promoted, which is said to be cost-effective and more flexible. And it can also ensure constant quality of the product because we are working in a steady state, so the batch-to-batch variability is lower. From the regulatory perspective, there are some new initiatives, among which the first was the quality by design. So this is basically aims to build the quality into the product instead of just testing it after the production. And this can be done by increasing the process understanding and also the identification of the process parameters. Critical process parameters. So what we want to do here is to establish a design space, which is a multivariate space of the parameters within which we can be sure that the quality is good. So the next initiative is the process analytical technology, which aims the inline and real-time monitoring of the production. This can be done by real-time analytical tools such as NIR or Raman spectroscopy, and also using multivariate data analysis and control. So if we manage to do the quality by design and the process analytical technology, then we can essentially be sure that we manage to produce the right quality. So there is no need for end product testing, and this is called real-time release testing. Another trend which is emerging is the Industry 4.0 or the fourth industrial revolution, and it's also making its way in the pharmaceutical industry called Pharma 4.0. So one aspect of this initiative is that we can measure a lot of things, and we can build a database. So for example, we can collect the laboratory information, the market demand, material and supply data, and of course the PAT data and manufacturing data. So once we have this database, we can evaluate them by mathematical models, such as with machine learning or artificial neural networks. And we can use these models, for example, to have a digital twin of the process, which can be used to simulate the process. And we can eventually have smart factories which can have adaptive control and autonomous decisions. So if we collect the right amount of data and we use the sufficient mathematical tools, then we can reach the wisdom from the process. So hopefully, as you can see now, mathematical models are getting very essential. So let's see what kind of models we can use. First of all, there are the monistic or multidimensional models, which are the most detailed but also the most expensive approaches. But they can be very useful, for example, for detailed descriptive models, process understanding, establishing a design space, or digital twins. Less detailed but also less expensive models are empirical or statistical models, which are, for example, the chemometric multivariate data analysis tools and the artificial intelligence and machine learning. This can be very useful for process optimization, real-time process monitoring, or control. So in this talk, I would like to talk about both the mechanistic modeling, mainly population balance models, and some examples from the empirical modeling. So mechanistic models, or also called first principles models, were used to a descriptive modeling of an active pharmaceutical ingredient production. So our model drug was aspirin, and we described this in an integrated continuous production, and these steps were actually created in the lab, so we had actual experimental data to fit the models. So the first step was the synthesis, where we used salicylic acid and acetylation, and then in the next step we quenched this reaction mixture with ethanol. So we used the reaction kinetics model to predict the concentration of the aspirin and also two impurities. And this was done dynamically, so we could predict the concentration at each time point of the production. At the next step, we used crystallization to get the solids from the reaction mixture. We used an anti-solvent cooling crystallization, and we described this with the population balance model, which essentially calculates the crystal size and count as the time goes, and we used the nucleation and growing of the growing kinetics of the crystals. After the filtration modeling and drying and capsule filling, we also wanted to determine the dissolution of the API because it's a very important quality attribute. We also described this by a population balance model where we counted the kinetics only of the dissolution. So with this model, we could calculate a lot of things. For example, we could count the effect of the components, the quantity of the components, and also the different temperatures. And we could calculate, for example, the conversion, the purity, productivity, the crystal size distribution, and the dissolution profile. So right now I would like to focus on the in vitro dissolution testing, which is used in the research and development to evaluate the in vivo performance of the drug. And it's also very important for a routine quality control test, for example, to assess the batch-to-batch consistency and the product performance. So having a model is very advantageous because we can calculate these very fast, and also because these tests can be very lengthy and labor-intensive, real-time release testing alternative would be very good. So with the mechanistic model, we could calculate what crystal size distribution is needed for a given dissolution, or when we have a given crystal size distribution, what will be the dissolution. But because we also had the crystallization process model, we could also calculate the crystallization temperature, for example, so what is needed to reach, for example, an immediate release specification. We could also calculate the productivity based on the crystallization parameters, and as you can see, if we increase the crystallization temperature, the productivity will be higher, but in that case, we can't reach the immediate release specification, so it's actually an optimization problem which can be solved with this model very easily. So basically, we established the digital twin of this integrated process which could be used for a virtual design of experiment. So this means that within minutes we can do thousands of experiments without the labor expensive processes. So this is the advantage of this kind of modeling. Obviously there are some disadvantages, and the main disadvantage is that such monistic models can be very complex. For example, we just model the dissolution of the API particles, but we usually have some drug formulation, for example, tablets. And in that case, we have to account a lot of kinetic steps. For example, the dissolution of the coat, the disintegration of the tablet, the deaggregation, and also the dissolution steps. So for this, we try to use an empirical modeling approach. And also I will talk mainly about the dissolution testing, but this approach can be used for any prediction of any kind of drug product quality prediction. So our idea was that we can collect PAT data and several process data from the formulation, for example, the tablets. In our examples, we use the NIR and Raman spectra, the crystal size distributions, and the compression force of the tablets. And we used artificial neural network to fit this model and predict the dissolution profile. So the advantage of this that these are very fast and non-destructive measurements, while the dissolution testing can take 20 hours. So the artificial neural networks, so let's see how this works. The basis of the neural networks are the artificial neurons, which can take any inputs and convert them to outputs. This is done by weighting each input and have a transfer function which converts them to output. In a network, we use several neurons in a series, and this is why how we can calculate the desired output. So we need a training data set where we have both the input and output, and with this we can optimize the weights so that we can minimize the difference between the calculated and the known outputs. So for this, we first screen the process parameters that are critical, and then we collected a training sample. We used the design of experiments for that, and then we collected the process data and measured the NIR and Raman spectra. Then we measured the actual dissolutions, and then we trained the neural network. We tested this approach using caffeine and drotaverine model tablets, and both were very good. We could predict the effect of several parameters, such as the API content, different excipient contents, the tablet compression force, and particle sizes. And as you can see in this figure, the validation samples was very so the results of the validation samples were very good. The model fitted very well the experimental measurements, which means that a 20-hour dissolution test could be replaced by a real-time alternative. So what was left is the testing of this model in real time. And for simplicity, for this we used aspirin capsules, which contained aspirin and microcrystalline cellulose. We continuously blended these two components using two feeders, twin screw continuous blender, and when the powder blend arrived to a conveyor belt, we also measured the NIR spectra in real time. So the problem was that the particle size of the MCC was overlapping with the particle size of the aspirin, so that's why we couldn't use the population balance model we previously developed, because that can count only the active pharmaceutical ingredient. So first we collected the calibration data set using different API content and different particle sizes of the API. And then we built some multivariate data analysis model. So we did a regression where we could predict the aspirin concentration based on the NIR spectra. Then we developed an artificial neural network which used the API concentration, which was predicted with the PLS regression model, and the particle size distribution as input. And then we predicted the dissolution as output. You can see the validation samples here that we got very good fitting. So what was left to test the model real time? So we did a half-hour blending, continuous blending experiment, and we started this experiment with feeding unsieved aspirin. And then to see if the model works, we added bigger and smaller particle sizes. And we could follow the aspirin concentration in real time and also the dissolution determined by the ANN. And as you can see, when we added the bigger particle size, the dissolution was slower, and when we used the smaller particle size, the dissolution was faster. So this is what we expected, so the model works. We could also detect by the real-time NIR spectroscopy that when we use the small particle size, the concentration wasn't good, so we couldn't reach the aim 20% concentration, which is so the small particles stick to the feeder, and this indicates a potential quality problem. So we can also use it for real-time identification of the error. So what's left, some conclusions. So we use monistic and empirical models to determine the product quality, and it's very important, obviously, to choose the right approaches based on, for example, the available experimental data and computational time, and also the aimed application. I mainly focus now on the in vitro dissolution, which is a very complex quality attribute, but the models still worked here, and I think this is a very important step to reach the aim of the QBD, PAT, and eventually the Pharma 4.0. So I would like to thank everybody who helped in this work, and also the financial support, and finally, thank you for your kind attention.
Thank you. Very nice presentation, and since the time kept quite nicely, we have a possibility to have some questions from the audience. Please.
Thank you very much. I can see now why you got the first prize for the last year. My question would be about the confidence bands on the artificial neural networks. How did you get that? So it's not an obvious process to get that, because it's a deterministic process. So if you have one neural network, it won't predict the confidence band by itself. So can you elaborate?
Yeah, thank you for the question. It was a very hard thing to start with that, but eventually we used bootstrapping. So we developed the 1000 neural network, and actually what you can see here as a result, it's an average of the 1000 model, and we could calculate the confidence band based on this sampling. Thank you.
Further questions? If this is not the case, then I congratulate again. Thank you for this very nice presentation. And I would like to introduce our next speaker from the Turkava Electric Institute of Technology, Attila Kovács, who is excuse me, Antal Kovács, without glasses, who is the chief research officer of the institute, and he will show us with some examples how industry and academia can cooperate on the electric industry technologies.
Thank you. This presentation will be a little bit different than today's whole presentation, because today in this conference you will hear about certain scientific topics, but my presentation won't focus on one topic. I would like to talk a little bit about industrial research. For that, I'd like to introduce the company I'm working for. Actually, I've been doing industrial research for 20 years. And at the end, I will show a couple of examples of scientific topics we are dealing with. But before that, I'd like to tell a little bit about my company, which calls Furukawa Electric. The company is an old Japanese company, headquartered in downtown Tokyo, and established in more than 130 years ago. And this company is globally presented, has about 50,000 employees and more than 100 subsidiary company around the world. You can see that companies presented in the United States, in Europe, of course in Japan, in Asia. So practically globally everywhere in the world. And this company is proud of some first in the world. So here I put a little bit about the history. As you see, it was established quite long ago, and this company was the first underground power cable, made the first underground power cable in Japan, and world first optical cable, for instance, or the highest voltage superconducting power cable. And not only first in this, but this company was also mother or father of many other companies. I don't explain all of that, but Furukawa Electric is in the middle, and just highlight a few. Okay, Furukawa Electric established Fuji Electric Company together with Siemens, and also Fujitsu company. So these are now bigger company than Furukawa Electric, actually. The company has now 5 business segments and 15 business units. So this means that the business area is quite wide. I will talk a little bit about that. But there are certain parts that are centralized in this company. So, of course, each business unit develops their own products and sell them, but some parts are centralized in the company, and one of them is the R&D. R&D is about 700 people in this company, and today I like to talk about this R&D organization. But before that, let me just explain a little bit about the products. You see some core technologies. What we have, these are metals or polymers, photonics and high-frequency technology. And this results many products. I cannot explain all of them, but I will go through very quickly on what kind of business and products we have. Okay, first is telecommunication, optical fiber cables, and not only the cables, but some connecting devices also in our business, like optical amplifiers or laser diodes or fusion splicers for optical fibers. Okay, the next is energy. These are power cables, different kind of cables and coatings. So here we have, for this we need to have good metal processing capability and polymer processing capabilities. And here you can see maybe some interesting thing like high temperature superconducting wires, or also low temperature superconducting materials are also in our product portfolio. The next is automotive products. Furukawa is one of the one big wire harness suppliers for passenger cars. But beside that, the company has sensors like battery sensor or radar sensor, or some special connectors like the steering rod connector, which is the largest manufacturer in the world. The steering rod connector is the connector when you drive a car. It's in front of you, behind the wheel, and this can connect the airbag and other electronic devices on your steering wheel. Okay, and next is the electronic products. You can see here many special wires or thin copper or foils. These are used in batteries or used in other PCBs or such things. Okay, and of course some construction materials is like pipes or tubes from metals or plastics. Okay, so you can see that we have a wide range of product portfolio. But I like to talk about the research. Okay, how this company organize the research? Of course, each business unit can do some product development, but there are some centralized research part, and these are organized into laboratories. And you can see these laboratories here. And some laboratories focus on certain area, but other laboratories focusing on just incubating new ideas. And these are, majority is in Japan, but a few is outside of Japan, and I'm lucky enough to work one of these laboratory in Hungary. It's called FETI. It's here. It's called Furukawa Electric Institute of Technology, and this is located in Budapest, and about 70 people is working for this part. But we have some R&D in the United States and in Japan, as I said. Okay, and what we are doing in Hungary? We have a very special mission. Our mission is to be in the forefront of the research and be the part of the R&D organization of the Furukawa, and in cooperation with its partner, we design, control, and manages and realize the effective use of scientific results in the industry. So what does it mean? We want to be close to the academic research as much as we can and apply its results in the industry. So in other words, when scientists write a paper, who will read that? Other scientists, it's okay. But at the end, you want to go to the application. In many companies, engineers are not enough, has not enough knowledge to read. So we are the people who read those articles and try to turn into some industrial application. So that's our mission, to make a bridge to the academic knowledge to the industrial thing. And in the Hungarian part, this FETI, we have 5 groups. You can see we have a simulation team. We do their basically our own mathematical models to support design and development. Some fields are like optical fibers or optical devices or mechanical thermal simulation. We have an automotive group where we are developing sensor algorithms. We have an advanced material group. They are developing new material properties, technologies, mainly experimentally. We have a nanomaterial science group where we apply high-level computational techniques. The leader is Tibor Hölzl. And we have an AI group where we try to industrialize machine learning techniques. There's a big hype around machine learning, but we want to find out what we can apply really in the industry. Okay, and I'd like to now talk a little bit about the difference between industrial and academic research. Okay, so when you think on that, there are some words that came into your mind, like research freedom or timeline or budget or publications or future application. Okay, I would like to start the main point of the difference. This is how we select a topic, selecting a research topic. I have a friend who is an assistant professor in a university, and I asked him how they select a research topic, and he showed such things like we need a problem, we talk to the professor, maybe he's some problem, we check some personal interest or scientific value, such things. And in our case, unfortunately, none of these really matters. In case of industrial research, there is one thing that's really behind the topic selection. This is the profit. So this is a private company. Each research is very, very expensive. So when we're spending money, somehow at the end, we have to have a vision how it will make a profit for the company. We have to make it very clear because, you know, production people working very, very hard for each dollar or each cent to make the profit, and we practically burning this profit with our industrial research, with the research. So this means that we have to be very, very focused on when we are selecting a research topic, and for that we use some technique to help us, or some methods to check our topics, and first called Ansoff matrix. So when a company thinking on their growth or new business, they usually investigate a so-called Ansoff matrix, which can help to analyze the strategy. And it shows 4 strategies and some risk with each of them. And let me just explain. So this matrix has 2 axis. One is the product and the other is market. So you can see that if we have an existing product, or we have to go with new product, we can go with new market or existing market. And just I like to explain this matrix with some example. But first, if we are going with the existing product, with the existing market, typically that's the safest thing. We would like to increase our market with, we call market penetration, or just not to lose something. So we do something development that's related to that. When we want to go for a new product with the existing market, we call that product development. This is a little bit more risky, of course. And also, if we go to the market development, which means we have an existing product with a different market, that's called market development. And this is, we consider same risk, but the most riskiest is we call diversification, when we go to a new product with a new market. And I will give you an example to make it clear. What does it mean? And the example will be very simple and not related to the chemistry, sorry. this will be an automotive product because I can easily explain with that. Okay, this is the automotive radar. I will show how we develop the radar, then how we change the automotive radar to infrastructure radar, and the first generation to second generation. Okay, so this is the radar. This is an automotive component now getting very, very common in most of the cars. The application of the radar this is mounted behind the bumper. It can help you to alert when somebody is in your blind spot. So when you change lane, it can give you an alarm. But there are additional applications like cross-traffic alert now getting more and more common. Okay, so Furukawa was a good manufacturer of wiring harness. That means that we have a good market on automotive product, automotive companies, especially in Japan. So the existing market is like Toyota or Honda or Mazda, or these companies. And if we're developing a radar, we can easily go to these companies with the radar and explain, okay, we can do this. Because they understand that we know the automotive standards. They understand our logistics and the way of our R&D. So this is this is not very risky to try to penetrate with the radar. But of course, it's very, very hard. Okay, so imagine we are succeeded with the radar. With a 24 gigahertz radar, somebody came up with the idea that this radar can be used not only on the car, but we can fix on the light poles or some buildings, and we can use it as a traffic counting. Because the radar has the capability, it was designed for detecting vehicles and pedestrians. Okay, it sounds easy, but this is a different market. In first case, our customers are automotive companies, but in this case, our customers like city operation companies, totally different companies. The volume is different, price is different. So this is, we have to understand that this is a market development in this case, okay? And to give an example to the market penetration, once we developed the radar, we still had to continue this development to make the second upgraded version of the radar. This needs also many effort and research to make a better radar. And that radar is going for the same customers or same market, same similar product. So we have to do this to keep our business. Okay. So these are that can help us to understand when we're selecting a topic. Okay, and when we start a project, we not only look this, but we also check some roadmaps. Some automotive companies have some vision about their future, how they will develop their vehicles. And we have to align, like if they have a vision of autonomous driving and some functionality of the radars, we have to follow or try to align to these developments. So that's why we are using so-called roadmaps. Roadmaps can be found in many topics in the world. Companies are thinking like on other topics. You can see such roadmaps. Many interactions. These are help us to understand where will be the future products, what technology is needed for that, what parts or components needed for that, so we can plan our development. We also plan our we also do so-called 3C analysis, where we try to understand the customer needs, our company strengths and weakness, and our competitors' movement. Without that, it's very hard to start. So these are all we have to check carefully before we initiating a new theme. And there's another thing is the technology readiness level. And the company should balance their R&D portfolio between these technology readiness. You can see when we are thinking on a research, that could be at very, very different level. Is it just an idea, or we are very close to something, to a product? What level is the technology we want to develop? If we develop only something very close to the production, then in long term we will have a problem. We will lose our competitiveness. Of course, if we are doing only just basic research, this will also make a problem on long term. So in Furukawa, we always classify our topics. We have very similar R&D thema classification, and we score them from many aspects, and this helps the leaders to make the decision. Okay, and the next, what is also have to do is checking the IP, intellectual property. So we have to do some patent search before starting a thema, because if our competitors patented some technology, that can make hard our life. And there are some techniques for that called patent landscaping, and this is also used to see this is the upcoming trends in the industry, or it's something other companies want to stop, or we can see the portfolio, who owns the majority of the patents on that field. And we have to also decide how much we open our trade secrets or knowledge. One way is when it's called open strategy, when we patent every idea we believe. The other way is the closed strategy, when we try to keep it as a trade secret. We have to decide also this. Both has an advantage and disadvantage in this case. So usually we also check these kind of things before starting the thema. Okay, and once we started and we could start our project, this won't go forever. In industrial companies, usually there's something like a phase gate model. So we have certain stages we have to achieve something, and the managers or some committee will make a decision to continue or not to continue the thema. So at each time we check, typically yearly, whether to continue or not to continue that kind of topic. So this means a very, very hard situation and hard pressure on the researchers. Okay, now I'd like to talk a little bit about some cooperation with universities, and we have many scientists with good engineers in the company, but we cannot keep, of course, all the competence at high level. So we do need to cooperate with universities or institutions when we want to bring the highest knowledge into the company. And in the next few slides, I will show some examples about when we are cooperating with universities. And but before that, just some history. Our past in Hungary is strongly related to the so-called composite insulators. These are silicon rubber insulators for high voltage cables. And in the history of the Institute of Inorganic Chemistry in the Technical University at Budapest has, I think you can find some backgrounds for this. Professor József Nagy has a lot of results in these fields, and at that time we also cooperated with them, but that was, I think, many years ago. But now we have different topics. First one is I'd like to show is some surface treatment of polypropylene. Here we prepared a polypropylene sheet and a special solvent treatment, and as a result, with some there's some phase separation here after the solvent treatment, and we can peel off a skin layer from the sheet, and as a result we get some highly hierarchical surface. You can see a scanning electron image on the right, And this results a very, very good super hydrophobic surface. And this is our invention, and we patented. And we cooperated with the Department of Physical Chemistry and Material Science, and we give them this surface for further scientific research, and they used some plasma treatment and modify the surface, and they can adjust the wettability of the surface, and they could change according to the techniques in different wettability. We can reach even 0 angle to 150 degree in the contact angle. Other topic is catalyst development. Furukawa is working together with Hokkaido University to develop a new catalyst that has a very different structure. The so-called supported catalyst structures has some drawbacks in the dry reforming reaction. So Furukawa developed the so-called Ramun catalyst, where these nanosite particles are embedded in a porous material, and this can help to help a little bit to keep the activity on long term, the catalyst, because for instance the coking will not happen. Here we are doing many calculations and simulation to understand the reactions on the surface of a nanoparticle inside a porous material. We also have a good cooperation with other European universities. We are part of a European Horizon 2020 grant, where we're working with the university, the Technical University of Budapest, and other European universities and institutions in catalytic hydrogenation of and electroreduction of CO2. So today, Professor Popper mentioned maybe we can solve the problem of the CO2. So we are working on that. Please, you can join these efforts in the world. Okay, so in this catchy consortium, together with Tibor Hölz and partners in the universities, we are working in such things like the reaction kinetics and transition metal doped copper clusters and CO2 activation on that. Okay, and to summarize, you can see that the industrial research has a lot of similarities to the academic. However, we have some differences, the topic selections, or aligned to some growth strategy, or balancing the technology readiness level, IP, 3C, such things. And but we need a good cooperation with the universities. And last, in academic research, you can fall in love with your topic, but you see in the industrial research, you cannot fall in love. So that's the only thing I missed from the industrial research, and I'm a little bit jealous to the academic people. Thank you for your attention.
And the floor is now open for having questions. This is a very nice opportunity to get direct contact with industrial researchers and research organizations. So please.
Thank you for your talk. It was very interesting. My question would be is how can a company like yours keep up with exponentially changing trends? Let me give you an example. So for example,
It's a hard question. There are several aspects. Our company has many business. So if one business somehow, let's say radar, we lose, the company will still go on. And the knowledge probably will be used in other products. The radar, when we started to develop the radar, we have no previous radar. The knowledge came from telecommunication. So like we had to design antennas, receivers, such things. So that was our background. So of course, if the market changing, we will give up that kind of thing. Just following so rapidly is not, I don't think we can be prepared for that. Research is a long-term thing. You do research, you see this is not from one moment to the next. Usually these have 5-10 years terms to achieve something from the idea to the product. So some topics fails, but some other topics will survive. So we will. It's like evolution. That's the sad fact. So that's why we cannot fall in love with our topics, because it can happen that they will be terminated. When I started to work at Furukawa, my first topic was related to optical fusion, optical fiber splicer, but the dot-com boom was over, and the optical fiber prices went down. The telecommunication business went down. So when I started, after 2 years, my thema was just terminated and said it will never continue. So we cannot fall in love. We have to be prepared for the next. Okay, I didn't talk about that, but let me just give a few words about that. Of course, the majority of our projects coming from Japan, but some parts we have some freedom, like a certain part of our resources we can decide by ourselves in Hungary, in FETI. We can make a decision to use for anything practically. And in that case, we use this resource to propose new thema. So we can make some experiments or some calculation, simulation, or feasibility study, and then we can propose for the central R&D division to initiate a new thema, because that needs much more resource. So we have much smaller resource. So both way exist, majority coming from our industry or coming from the head office, okay? But a small part we can initiate. So we are lucky that we have this opportunity to initiate, yes.
Thank you so much. And since time is running, I thank again this prize lecture. Show some research presented by
And in the next couple of minutes, I will talk about chronitors. It will be a journey in catalyst development, which is still in progress. As we know, catalytic processes are important in organic synthesis, and a special case of heterogeneous catalysis is phase transfer catalysis, in which the reaction takes place between immiscible phases, and the passage of one of the components is facilitated by the catalyst. The catalyst can be a chronitor, and the chronitors can differ from each other in the ring size, in heteroatoms, or in the structure. Chronitors can contain chiral units, and in this case they can be used in asymmetric synthesis. The first chiral chronitors were prepared from binol and butane diol, and these are artificial compounds. These cannot be found in nature, but for chiral chronitors, natural compounds can be used for the source of the chirality. As you can see in the slide, compound 3 and 4 contains sugar alcohol units, mannitol and tritol. Our research group uses also sugar alcohols and monosaccharides to synthesize chiral chrome compounds. Carbohydrates have advantages, such as they are cheap and readily available compounds. They have lots of functional groups, and the chirality can be diverse. During the development of the chrome catalyst, the structure effect relationship was investigated, and for the investigation lots of compounds were synthesized. For example, chrome compounds containing 2 carbohydrate units and chrome compounds containing 1 or 2 nitrogen atoms. During the testing, it was found that chronitors having monoaza chrome 5 structure are the most effective, and they were effective in a certain model reaction. After it was realized, this structure was in the focus of the development. Let's see how to synthesize monoaza 15 chrome 5 compounds. First, a compound is required that contains 2 free hydroxyl group, and the other functional groups are protected. After a podant structure is created using double O alkylation, and the next step is a halogen exchange from chlorine to iodine, and the ring closing step can be realized using primary amines. Depending on the structure of the amine, different chronitors can be synthesized, which have different side arms on the nitrogen. This side arm is important in the complex forming process, and depending on the side arm, the enantiomer selectivity can be different in the reactions. We experienced that when the nitrogen contains a hydrocarbon unit as a side arm, these compounds cannot generate high asymmetric induction, but when heteroatoms are present in the side chains, or different functional groups, it was found that hydroxypropyl, methoxypropyl, and methoxyphenylethyl groups are good for the enantiomer selectivity in general in the model reactions. The 15 chrome 5 compounds can be altered not just on the side chain, but at the different points in the structure. For example, the protective groups in the 4-6 position of the carbohydrate can be changed, and it was experienced that as the flexibility increases in the chrome structure, the enantiomer selectivity decreases in the reaction. Another point for the structural modification is the Anomeric Center. Not just the position can be changed on the Anomeric Center, but the substituents also. It was experienced only a slight, a little change can affect dramatically the outcome of the reaction. And of course, if we change the carbohydrate backbone of the compound, we can get different results from the reaction, from the reactions. Not only glucose can be found in nature and used as the source of chirality, but other carbohydrates, for example, mannose and galactose, and from these compounds different structures were prepared. Another compound is maltose, which can be synthesized easily from glucose, and not just 5-membered carbohydrates can be used as the source of chirality, but 4-membered, for example, arabinose, and different hexapyranosides can be synthesized from other carbohydrates to use in chiral chronators. Hexapyranosides can form not only pyranose structure but furanose also, and based on different furanosides, chrome compounds were synthesized, and it was found that these structures are not so effective in general in terms of the asymmetric induction. Interestingly, it was found that these chrome compounds can form a strong complex with silver ions instead of sodium. And as I mentioned, not only monosaccharides, but sugar alcohols can be used to synthesize chrome ethers using the easily available mannitol as the starting material. Different structures were synthesized, and it was experienced that depending on the protective group of the carbohydrate, the enantiomer selectivity was different. And the other simple sugar alcohol is tritol, which can be synthesized from tartaric acid. And using this sugar alcohol, also lots of crown ethers were synthesized, which was tested in different model reactions. And as I mentioned, the main goal is to perform enantioselective reactions using carbohydrate-based crown ethers. We use simple reactions for testing the carbohydrate-based crown ethers, and there are two main types from model reactions. One is the liquid-liquid two-phase system, the other is the solid-liquid two-phase system. We use a small-scale reaction to test the crown compounds, and after the product is isolated, the enantiomeric excess is determined by HPLC or NMR measurements. The first enantioselective reaction was performed more than 40 years ago by Donald Krem using binyl-based compound 1, and this product was isolated after the successful reaction with 99% enantiomeric excess. One of the model reaction which we use testing the crown ethers is a liquid-liquid two-phase Darzen's condensation, and for this reaction we use 2-chloroacetophenol and benzaldehyde in the presence of a strong base and crown ether. This was the first enantioselective reaction which was tested in our research group. Using glucose-based crown compound 9H, the enantioselectivity in the product was 62%. When the protected group in the 4-6 position was changed, the enantioselectivity generally decreased, not only with compound 14, but with the others. When the change was in the anomeric position, we can see the enantioselectivity was affected, and the product 34 was formed with higher enantioselectivity. And I forgot to mention, this reaction was performed with complete diastereoselectivity. When we changed the source of the chirality from glucose to galactose, we experienced that in the case of the compound 20A, the enantioselectivity was lower than in the case of 9H. But when the anomeric center was altered in the position and in the substituent, the enantioselectivity was higher. And in the case of sugar alcohols, we could reach the same enantioselectivity that it was measured with compound 9H. Other model reaction which was used for testing crown ethers is the liquid-liquid two-phase epoxidation of chalcon. And in this reaction, compound 9H provided the product with excellent enantiomeric excess. With a slight change in the structure, when the protecting group in position 4 and 6 was changed, the enantioselectivity decreased. And this was also a general formula. When the anomeric center was altered in position or in substituent, this also affected the enantioselectivity, but it was not. There was not so big difference that it was in the case of Darzen's condensation. When different sugars were used as the source of chirality, we can see that in the case of mannose-based crown ethers, interestingly, enantioselectivity was high, but the enantiomeric preference was altered. The other enantiomer was formed in excess. In the case of galactose-based crown ethers, similar structure provided lower enantioselectivity. And surprisingly, when the position in C2 and C3 was altered and the ultrarose-based chronometer was used, there was practically no enantiomer selectivity generated in this reaction. When we used a different system, a solid-liquid two-phase system, it was we get different results. One of the reactions which we use testing for chrome compound is the Michael addition of nitrostyrene and compound 37. And using chrome compound 9H, which is still the most used and generally the most successful chrome ether in our research group, the product was isolated as a single enantiomer. When the side chain was altered just a little, the methylation resulted in the decrease in the enantiomeric excess. When the ethyl group, methyl group was changed to an ethyl group on the Anomeric Center, the asymmetric induction was again lower. Using galactose-based chrome compounds, we can see that structure 20A is the analog of 9H, and the enantiomer selectivity is quite similar. And when the terminal hydroxy group was methylated, the enantiomer selectivity decreased, but the value is still higher than in the case of 9J. When we use the sugar alcohols as the source of chirality, chrome compounds derived from tritol generated high enantiomeric excess, but when the hydroxy group was replaced by a methoxy group, the enantiomer selectivity was lower. Recently, we tested such kind of Michael additions in which the Michael addition step is followed by a ring closing step. And in this reaction, different cyclopropane derivatives were formed. And as you could see from the presentation, each reaction requires a different catalyst to reach the highest enantiomer selectivity. And it was the same in these cases. For the first reaction, a galactose-based chrome compound was selected, which generated the highest asymmetric induction. And a different chrome compound, a different galactose-based compound was the most successful one in the second reaction. And also a galactose-based one, but with different side chain and with different anomeric substitution, was the one which generated the highest asymmetric induction in the third reaction. And the main problem is also the robustness of the reaction, which can be experienced in the catalysis. And just a quick example about the robustness: if we use the unsubstituted compound 39, we can reach using 9H, the catalyst 9H, a low enantiomer selectivity. But when we use a substituted aromatic ring, the position and the substituent also affects the enantiomer selectivity. And when only two atoms are one atom is different in the compounds, we can see there are huge differences in the asymmetric induction. And if we use different aromatic rings, we can see that the anti-selectivity also depends on the nature of the substituent. And finally, I would like to thank everyone who participated in this group and for the organizations also. This presentation was not only one man's work, but it was the group of, it was a teamwork. And finally, I would like to thank you for your kind attention. Yes, we used different bases or different inorganic compounds, but the results remained almost the same. It was mainly dependent on the structure of the catalyst, not on the inorganic compound.
So thank you for this nice lecture again. The next speaker, this early morning session will be Victoria Fag from the Department of Applied Biotechnology and Food Science, who will show us the results of the bauxite residue reuse. I think this research stemmed from that accident at the mines.
We will see.
So we are looking forward to learn how can we use this residue. Thank you so much.
Thank you very much. So I will present nearly 15 years of research today. Of course, it was not done by me, but the whole research group of environmental microbiology and biotechnology. So firstly, what is bauxite residue? This is the waste generated during alumina production. It mostly uses the Bayer process, which is the digestion of bauxite ore in hot sodium hydroxide. Therefore, it has highly alkaline characteristic, and it's stored worldwide in huge quantities, and basically this is increasing every year, the amount of bauxite residue. So as I mentioned, it is highly alkaline. It mainly contains iron oxide. This is the name red mud also comes from this. Also, although it is dependent on if it is stored in a mud form, we can call it red mud. If it's dried a little bit more and stored in that form, it is better to call it bauxite residue. As you can see, it also contains aluminium, titanium, and of course sodium. It also contains some economically important elements such as scandium, gallium, vanadium, and rare earth elements. There are some potential applications for bauxite residue. It is highly studied. It came into focus, I would say, in the last 15-20 years, that we should reuse this waste and not store it. And one of the main reuse option is in the construction industry, so as an additive to cement. But it can also be used in chemical industries, for catalyst, adsorbent, or also additive and coating pigments. This also comes from the red characteristics, so the iron content. But we were focusing more on environmental and agronomical applications. It can be used for the treatment of wastewater, waste gas, and also soils. So we were working with soils, and also it can be used for either contaminated soils or degraded soils. And recently we were focusing a bit on the metallurgical applications, and especially the recovery of minor elements from bauxite residue. So this waste can have either some advantages and disadvantages characteristics, also, although it depends on the reuse option that we choose. But mainly we could say that sodium content, high pH, the toxic metal content may be problematic. Some bauxite residues are radioactive. That is also a problem, especially in the construction industry. And it has small particle size. And as mentioned in the introduction, there are some problems with disposal. Either they are stored in a mud form, or for example, if it dried out more, then there are dusting problems. So there is not really a good solution for storing this material. However, in certain applications, the elevated pH, the particle size, and the related larger surface area, also the micronutrient content such as phosphorus may be beneficial, and I already mentioned the economically important element content. So now the story begins. So our first encounter with bauxite residue was for soil treatment for contaminated soils that were contaminated with toxic metals. And, So bauxite residue can be applied as chemical stabilizer in soils, meaning that they immobilize metals in the soil so that they become less available for plants, microbes, and also less leachable with, for example, rain. And we use this methodology in the György mining site. It was an old lead and zinc ore mine that was abandoned in the 1980s, basically. And there was a huge area contaminated by mine waste that were left on the site. And also the agricultural area was contaminated due to regular floods in the area that brought the contaminated waste into the agricultural lands below the György village. So this was a huge remediation project, basically, and this was only a part of it, this technology called chemical stabilization. We tested various stabilizers in the soil, for example, some traditional ones, and also waste such as fly ash or the bauxite residue. We tested them in small soil microcosm experiments. And just to highlight some results, you can see that the various fly ashes were quite, this is the decrease in metal mobility. So you can see that these were highly capable of immobilizing metals in the soil, and also decreasing plant available zinc and cadmium, which were the most problematic metals in these soils, and also reducing plant toxicity. The bauxite residue is here, so you can see that there is a potential in using it also for a chemical stabilizer in soil. Especially it can decrease the acetate extractable, so the acid-soluble fraction of metals in soils, but it was not successful in reducing toxicity or plant-available metal content. So finally, we didn't choose this as the main option for the treatment, for the field experiments and the field treatment. What we went with the fly ashes instead. And actually, this was my PhD work, or part of my PhD work. And then, so everyone remembers the Oláh catastrophe in 2010, on the 4th of October, when the 10th cassette of the red mud storage facility of the Oláh, or the MAL, alumina plant broke and released a large amount of red mud into the environment, affecting large areas of land and villages, and unfortunately the people's life who lived in this area. And during this, when this catastrophe happened, the former leader of our research group, Katalin Gruiz, was asked as an expert to find out what to do with the flooded areas, and especially focusing on the soils. And back then, in 2010, there was not so much in the literature on the effect of red mud on soils. So we carried out like really small microcosm experiments. We mixed red mud into the soil from the affected areas, and so what happened? So I don't want to go into details, but here you can see the inhibition percentage for various ecotoxicological test organisms. And what we basically found that up to 5%, maybe up to 10%, bauxite residue can be mixed into the soils without having serious toxicological effects. Of course, our decision also depended on other experiments like metal content and other studies. And we also participated in the risk assessment of the flooded sediment with a group from the UK. I don't want to go into details. There are some really nice publications on this. They come back 3 years after the catastrophe. They checked what's the status of the rivers and the river sediments or the creek sediments, and they found out that the remediation was quite successful and only a few remaining hotspots could be found in this area. I'm sorry, but I don't know the status, the current status, so don't ask me about this. So our focus turned to bauxite residue, if it's possible to reuse it. And we carried out in several projects experiments for reusing bauxite residue as a soil amendment, and especially acidic sandy soils. This is quite common some parts of Hungary, for example, in the middle areas. And just some results. What you can see that, of course, if we mix bauxite residue in different amounts to the soil, the pH will increase. But this is, in case of acidic soils, it's very favorable to reach the near-neutral pH. It also increases, for example, water holding capacity of the soils, which is very bad in case of sandy soils. And just to show you some microbiological results, what we found that in 5 and 10% on the short term, it increases this is the control, so it increases the microbial activity of the soils. We also use bauxite residue as a component for artificial soil. This experiment was done in György at a municipal landfill site. So we basically created a landfill cover. And here, what we found out that in this controlled environment, like 20% bauxite residue can be mixed with soil or a low-quality soil, and create a cover where we could, grow really nice grass or plant cover in these landfill sites. Recently, what we were working on is the extraction of some valuable elements from the bauxite residue. Some are considered critical raw materials in the EU, meaning that we have either a supply risk and also high economic value for these compounds. And the first attempt to do this for bauxite residues was done by Eva Ujacki, a PhD student, and she used selective acid leaching followed by liquid-liquid extraction to see if we can extract these elements from the bauxite residue. We also have an interest in biotechnological options. It is called bioleaching, when we use microorganisms for the extraction of elements from a certain solid material, usually ores. And for example, we can use penicillium species, which fungi produce organic acids, or acidithiobacillus species as an example. These are autotrophic microbes that produce sulfuric acid. These are iron oxidizers. We also had a study to see if there's something living in the bauxite residue, if it's possible. So we were searching for extremophilic microorganisms. They are called extremophilic because this is an extreme alkaline environment and with high sodium content. And these are some examples. We were able to isolate and identify some of the microbes. You can see that some has quite high pH tolerance, salt tolerance, and they have some potential biotechnological interest, like producing siderophores or able to mobilize phosphorus and so on. Last but not least, we participated at the H2020 project. This was very interesting for us to be part of this large European project. It was focusing on the extraction, refining, and production of scandium from various wastes, including bauxite residue. You can see some examples that scandium can be applied in lasers, solid oxide fuel cells, and also it has nice advantages in aluminum-scandium alloys because it is lighter than aluminum. So there was an interest from the aviation industry in these alloys. Here, what we did, we applied the concept of green ecotoxicology, basically. That means that we have an ecotoxicology lab here in our department, and we used various test organisms for the testing of waste materials that are coming from these chemical processing. And I would call it green ecotoxicology because we use it during the development so that we can alert chemists if there is something wrong. For example, in the waste, they become more toxic, for example, than the original one. They constructed a pilot plant in Greece, in the methyleneous alumina and aluminium plant. So where the first step was a leaching unit, and here, after the leaching, there is still a solid residue remaining. So we wanted to check if it's more toxic or less toxic than the original one. And it was quite a successful project with the solvent. So it was followed by a solvent-impregnated resin technology, and they produced the crude scandium hydroxide at the end of this pilot demonstration plant. It's still in operation. This is basically the first in Europe. So we use this ecotoxicity test battery, including bioluminescent bacteria, the famous Daphnia magna, and also some plants. And basically, just to show you how it works, we tested the bauxite residue, and then we got samples from partners, so to test the residues from the extraction steps. Then they went for lower sulfuric acid content due to economical reasons, and finally they chose this for the pilot plant. What you can see is the effective concentration values causing a certain amount of inhibition. This was nearly the same. If it's the higher, in this case, it was more toxic. So the sample was most toxic. So it was nearly the same. They had both slight acute aquatic toxicity. So this is a summary of the research done in our research group. So we started with metal immobilization, followed by participation in risk assessment. Then we started to use bauxite residue as soil amendment and in artificial soils, and recently as a source of valuable elements. So I also asked myself the question, what is next? I think one option could be the complex reuse. For example, in this Greek plant, they are aiming for this. So hopefully, maybe after the extraction of valuable elements, we can still use the residue for construction or even agronomical purposes. And also, I think some environmental sustainable applications, such as bioleaching, could be an option. And I thank very much my co-authors. Again, this is not the work done by one person, and also thank you for your attention. Yes, it's very much different, and it's dependent on the bauxite they use. So actually, this was a problem that, for example, in this big plant, it's changing constantly. For example, they have some Greek bauxite, but they also have Jamaican bauxite processed, and depending on their mixture, actually the characteristics change very frequently. There is a big difference, for example, the Hungarian bauxite residues. We have some in Almás, Füzítő, Mosonmagyaróvár, and Ajka. They are all different. So also it dependent if it's a fresh bauxite residue or it's stored. Of course, the metal content is not dependent on that, but other characteristics are dependent. So it's a problem. You have to make processes that are quite flexible for the changing characteristics.
Thank you very much. I would like to thank you for this very nice presentation, for all the early morning session lecturers. Thank you again for that. And now we have a coffee break, but I should tell you that this coffee break would not be possible without our sponsors, who are Aegis, Perform, Soltec, and the József Varga Foundation. You will see quite soon who supported that coffee break. I think the coffee break will be over there.
Thank you very much, Professor Nyulassi, for this kind introduction, and also to the organizers of the Oláh György Conference, or György Oláh Conference, to give me the possibility to present some of the work of our research group. So when anybody thinks of porous carbon, what comes in your mind immediately, that it's black, it has a high surface area, it has a hierarchical pore structure, and thank you. And also that, oops. Okay, yes, I got it. Okay, but that doesn't turn the page. No problem, fine. Okay, thank you. Okay. Oops. De én nem akarok, azért fordította meg a gépet, hogy nem kell léptetnem, mert a géppel fogok léptetni.
Ja, jó. Jobb a fénye.
Rendben van, de azt nem értem, hogy én jó, most már látom a fényet.
Sorry for the complication.
No problem. So, even at the technical university, you may have technical problems. So, and it works through secondary forces. So this is well known also for humans, that it can work also as solve digestion problems or food safety problems. Recently I found a little movie, but I do not want to show here, I do not want to spend the time with that this information, that it can be used to solve digestion problem or for antitoxic, as an antitoxic agent, is also known by monkeys in Zanzibar. So they love just the leaves of exotic fruits, but that makes them, due to the phenolic compounds, that makes them stomach ache, and they were shown to eat charcoal from the woods or from human areas, what they found, to heal their problems. So this is, but this is not what I wanted to talk about. I'd like to go a step ahead, because these carbons have not only morphology, but they also have a surface chemistry. That's not a very, very long information that was discovered in the late 90s, the last century, when they couldn't solve the question of carbon-supported catalysts, as they became somehow, so they had to go back to the surface of the carbon, and then they found that the most frequent heteroatom on the surface of carbon, of course, it cannot be avoided, the oxygen, which comes from the air. Hydrogen is not considered as a heteroatom, though. And so they found quite a lot of progress in the last century, and also we see that we can find all the oxygen functional groups, what you learned in in organic chemistry, and also due to the presence of these oxygen-containing functional groups, the carbon surface also behaves as an amphoteric surface, because it can protonate and deprotonate depending on the pH of the medium. Also, that's interesting that please realize that in porous carbons, the oxygen always decorates only the edges. So no oxygen incorporation in the graphitic layer. So the next step, however, that's the problem of fuel cells, and I'm happy that there are the next two talk will be related to electrocatalytic applications. And so in fuel cells, you know that the oxygen reduction reaction is one of the main driving forces of producing energy in this way. And there are two pathways. For that, one is there is a faster with 4 electrons, and one is another one with 2 electrons, 2 plus 2 electrons, and that's a slow process. So to enhance or to speed up the process, they use platinum. platinum makes all these solutions much more expensive, so a way to avoid the application of platinum, or at least to reduce the application of platinum, is to decorate the carbon with nitrogen atoms. So nitrogen atoms are very challenging, so they are just one step away in the periodic chart. So they have a different, higher electronegativity, they have more electrons than the carbon, so it means that their incorporation creates active sites which are benign for this, or considered to be benign for this oxygen reduction reaction. So however, nitrogen can be built not only around the peripheries, but also it can be incorporated into the local, the carbon, the graphitic or graphenic carbon sheet. So there is still some ignorance about what type of nitrogen is the most advantageous to promote the oxygen reduction reaction. So you may see that the literature is pretty confused about that. So we started to get interested in nitrogen ourselves, because in previous studies with carbon nanotubes, etc., we found that nitrogen-doped carbon nanotubes were very active in hydrogen peroxide decomposition. So the first thing is, when you wanted to spare some experimental time, that you do quantum chemical calculations. These calculations were done in Professor Kállai's group and by Adam Gonyec, and he found that couldn't find any specific nitrogen position, though he concluded that any type of nitrogen inbuilt into the structure enhances the performance, because it creates new active sites independent what is the position of the nitrogen inbuilt. Of course, there are always limits of the calculations. In this case, that was a single nitrogen incorporation and no other functional groups were considered. Also, we see that nitrogen, if there are too many, then it might be might have a negative effect. So carbon aerogels, which I think that one of the, for me, that the very impressive material. So we were able to prepare highly porous carbon surfaces with tuned nitrogen content, and with the melamine resorcinol ratio, we could go up from 0 up to 1, and we were able to study the influence of the inbuilt nitrogen, because although the, I would say, macroscopic scale, or the macroscopic picture of these carbons are pretty dissimilar, as you may see from these images, but their nanostructure, which comes from the nitrogen adsorption isotherms, was pretty similar. So what we found, that we had the same similar pore size distribution, and we couldn't find any particular difference in the nanoscale morphology. So we could say that we studied the effect of nitrogen on a set of carbons which have a similar morphology. So first of all, what we found, and that is seldom characterized in the literature, people use XPS for surface chemistry. However, if you compare the bulk and the surface composition of our carbons, it's pretty similar. So in the upper So this is the full symbols are the XPS, and the open symbols mean the surface composition, and the red is for oxygen, the black is for nitrogen. So what we found that particularly in case of the oxygen, there is a big discrepancy between the external and overall composition. That's not the case in the nitrogen, at least not in our case. But normally it's not checked in the literature. Also, if we look from XPS, where we can do that, for the composition, what we found is that the quartet nitrogen was the dominant, so that is when the nitrogen is built in the graphene layer. So because of this similarity, we use the bulk elemental composition to show that in case of the nitrogen, we found a pretty nice correlation between the external and total nitrogen content, which is not the case in oxygen. As for the electrochemical performance, so we use the CV curves to do the evaluations, and the good news is that the electrodes made of our carbon were relatively stable, and the onset potential was not very great, so that's about the same of a PN, a polyacrylonitrile-based carbon. But we couldn't find any nitrogens, couldn't distinguish any nitrogen species which performed better or gave a better relation than the overall nitrogen content. What was also found to be important, that the accessibility of the functional groups might be a crucial question, so a very important factor in the electrocatalytic process. So that leads me to my summary, so that porous carbon performance, by now we know that it's governed together with the porous texture and the surface chemistry of the carbon, and the oxygen functionalities and the delocalized electrons govern the acid-base properties, as I showed that briefly. And nitrogen fosters the oxygen reduction reaction activity in the fuel cells, but we still do not know what are the most, if there is any, the most important or most active nitrogen sites. There is a possibility, what was found in case of oxygen functional groups, that the presence of one or several types of nitrogen and the confinement coming from the pores might work in a synergism to promote this process. So that, let me acknowledge my colleagues, some international cooperations, also as I already mentioned, Ádám Ganyec, the gels were synthesized by Balázs Nagy. We used the CV facilities of the TTK with the help of István Bakos, and the XPS was done in Spain in the Carbon Institute Oviedo. And of course, the technician of the lab is the most important person in this presentation or in this work, and I also would like to acknowledge the financial support for our research. And thank you very much for your attention.
We have time. Thank you very much. The first question, so what is the relation of this round church and Öskü? It's a beautiful Romanesque church, by the way.
Yeah, it is. And so the story goes back a little bit. The yearly carbon conference this year was held in London. And in the Serpentine Gallery, there is always an open-air installation every year. And this installation is a church, actually. And there is a description that what was that inspired. And this little church was mentioned, that was one of the inspiration sources, yes. And I found that they are very nice core structure. So, yeah, cylindrical core, so that
Yes. I have one more comment on your slide number 5. This is nothing related to the results, but you have the nitrogens, those which are encircled there in a 6-membered ring, 2 tri-coordinate nitrogens, which should then contribute to 2 electrons to the ring system. So altogether, this ring system should be anti-aromatic and not aromatic, this particular ring. But I think it doesn't matter because they should be considered together. So all for this large system, these 2 electrons are somewhere distributed and not particular in that ring. But it's just a convention to write the circles.
Yeah.
Just
So what they claim that if a nitrogen is in those positions, those are considered as quaternary nitrogens.
Yeah.
But I think that all the electrons which are given by nitrogen in the system, they get delocalized and they mainly push the neighboring carbon to the electronegative difference to create an active site.
okay. It's just
Thank you very much. Thank you.
no other question. Then we would like to thank again.
Thank you.
Before we continue, since Christina is here and she is the editor-in-chief of the periodical Polytechnica Chemical Engineering series, so I have to announce that all the lectures presented this morning or in the afternoon by the PhD students are welcome to submit their work in periodical Polytechnica.
Thank you very much.
Okay.
Yeah, I think that we agreed with Dr. Kálai. Yes.
Okay.
Yeah.
Thank you very much again. And,
I hope it will be. Thank you very much for the invitation to this conference. Okay. Maybe this is better this way. Can you hear me at the back? Okay, thank you. Okay. I have to come here so that I'm visible to YouTube and the world. I'm pretty sure multiple million people will watch this after a while. All right, so what I'm going to talk about is electrochemistry and the application of different pretty new methods in this field. But first, I want to zoom in from a little bit of wider perspective, and it's the question: what is the best model that describes an experimental result? I think all of us face similar questions in our research. Let's look at this data, and you can see that, okay, it's not linear. What you might want to do is to linearize. Don't do that, okay? Linearization in the recent years have been shown to destroy the error structure, so it's not a good idea. But what you can do is to fit the model, okay? But what if you don't know the model? So let's say that we are not aware that this is the Michaelis-Menten kinetics, okay? And we want to go for polynomials, okay? So let's try linear. Okay, it doesn't really look good. Second order, third order, fourth order, fifth order, sixth order, it's even worse. But the strange thing about it is that if we look at the residual sum of squares, it decreases. So if we basically, we want to look at which is the best fit by a naive approach. Then we should say this is the best fit, because that has the lowest residual sum of squares. Obviously, that's not the solution. So there is an information criterion called Akaike information criterion. He's a Japanese mathematician who came up with the term. And he suggested to use this equation here, which penalizes the parameters. So if your model has more parameter, then it will be a worse model, okay? So this is a little bit like Occam's razor in philosophy, if you're familiar with it. Okay, so that gives us this AIC, this Akaike information criterion, and that gives us that around the third order polynomial is what's the best model. But if you look at it, you can see that, okay, this is not the case. We are still not good enough. And this is the part that comes in now. It's the symbolic regression. So what you're doing is pretty similar to nonlinear regression, but here you're not regressing your parameters, but you're working with equations, okay? So you're trying out, with the genetic algorithm, many different algorithms. And by recombining working algorithms, you can get a new algorithm. So you divide it, multiply it, and try out different algorithms, and the one that gives you the best fit is the one that you choose. And the good thing about this is that this is a white box technique, which means that you can look at the equation and you can understand what happens there. So it's not like an artificial neural network where you have no idea why it works. Here, you will get an equation at the end. So let's have a look at my example, my first example, and you can see it here. So these are the second order, first order equation, and you can see that the first order AIC is minus 48.9. Okay, so it's not bad, but it's not too good either. The second order is minus 26.2, but we want the lowest possible value. And this symbolic regression came out with this equation, which is the original equation. This is the one that the data was simulated for. And you can see that it has the best AIC value. And the symbolic regression came out with another equation, which is mathematically equivalent, but since it has one more parameter, its AIC value is a little bit worse. So the lower the AIC value, the better, okay? So from this, we can say that, okay, this is the equation that works. And indeed, this was the simulated data. Okay, but we don't have such a simple system for all of our studies. So this Mihaly-Menten kinetics is a system that can be described with one single explicit equation. But in electrochemistry, we have much more complicated systems, which change in time. We have diffusion, we have heterogeneous rate constants, we have different layers, glassy carbon, polypyrrole, ion selective membrane, sample solution, and they work together and will give you a totally complex system that is very hard to describe. So what can we do then? Or why we can use that? Okay, so first, we need a model. We need a model that can describe this system. The state-of-the-art model is the Nernst-Planck-Poisson model, which takes into account everything that can be taken into account. So migration, diffusion, heterogeneity, so everything like that. And what you can do if you have a model like that, you can do the normal problem. You can solve the normal. The normal problem is when you know the parameters, you know your system, and you simulate it. Okay, so in quantum chemistry, it's most of the times this is done. So we know the system, we know the parameters, and we want to see what happens. But in industrial approaches and in many applied sciences, this is not what we want. We want the parameters. We want to know the diffusion coefficient that describes our system. We want to know the heterogeneous rate constants that describe the system. And that is what's called inverse problem. To solve the inverse problem, we don't do just one simple simulation. We need to
do a global optimization which can take thousands of simulations. And this Nernst-Planck-Poisson simulation takes minutes or even hours to complete. If you need to do 100 simulation or 1,000 simulation, it can take weeks. So that's just not gonna work. This is an experimental and simulated impedance spectroscopy result after the fittings. So you can see that the fittings were quite good, but this took like 3 weeks to complete. So what can we do? We can either use a multi-layer perceptron, and I don't need to introduce it, luckily for our first talk, thank you very much. But the difference here is that this is a multi-layer. This is a deep neural network. The advantage of deep neural network is that it can automatically extract relevant information in the layered structure. Okay, and what we do here is that we put in the first layer frequency, diffusion coefficient, rate constant, so the parameters that we know. And in the output layer, we have the complex impedance. And we don't really care what happens in between the two, okay? So that's magic. That's artificial neural networks, okay? But it works remarkably well, okay? The other possibility is to use the symbolic regression. What is the advantage of the symbolic regression? Again, we will get an equation that we can look at and, oh, okay, that makes sense. That's why it works. All right, so let's have a look at the symbolic regression for the system that I've just shown here, okay? So this is it. So this is the symbolic regression. This is the equation that describes our model. I know it's a little bit scary, and this only describes one part of the complex impedance, the real part, and the imaginary part is even longer than this, okay? So it's long, but what you can do is to put this equation in Excel, and it will calculate it for you. So you don't need a sophisticated model in order to work with it. This can be inputted in Excel, okay? But with this, or the neural network, we can solve the inverse problem in seconds instead of weeks. Okay, so if we wanted to use the normal method, which is a FEM simulation with the Nernst-Planck-Poisson method, it will take weeks. This way, we can get it in seconds or even less, maybe milliseconds. Okay, and I want to show you something. Okay. So this is the impedance of the solid-state ion-selective electrode, and what you're seeing here is the working of this deep neural network. So what happens if I change the diffusion coefficient? You see? I can change the diffusion coefficient. What happens if I change the other one? What happens if I change the diffusion coefficient of the polypyrrole? What happens if I change... okay, so this doesn't do anything. That's good, because it shouldn't. But I can change many, many different parameters here. And you can see that it influences different parts of the impedance. So what I've done here, showing this little animation, would have taken weeks of simulation with the regular Nernst-Planck-Poisson model. This way, I could show you in real time. Okay, so that's the huge advantage of using machine learning methods. And there was one point in the first talk that machine learning models are good and fast, but they are not accurate. Sometimes it's true, but it depends on your setting. Sometimes they can be as accurate as your simulation. And I will show you that. Okay, so that was just for the impedance spectroscopy of an ion selective electrode, but this can be done for a battery model, which has maybe a little more industrial reference, at least in the 21st century. So what I'm doing here is a model, a pseudo 2D model of a battery. And what you can do is also getting the impedance spectrum. Impedance spectrum is very good because it has many, many characteristic parts which can be used to understand what happens in the battery. Okay, so here we simulated fresh battery. Here we simulated aged battery. And what you can do is you can simulate different batteries with regards to the charging. Okay, this is the state of charge. 0 is totally discharged, 1 is totally charged. What happens if I change the particle size? This happens, okay, that changes the whole structure. But this can be measured also. Okay, so this is an experimental complex impedance of the lithium-ion cells at different SOC, different charge levels. And you can see that they are similar. Okay, not the same as the simulation, but they are pretty similar. What we did here, we did the same. So we trained a deep neural network in order to understand the impedance spectrum of a battery, okay? It took more than 150,000 different frequency simulations to get a good model. So what happened is that randomly batteries were simulated with this kind of diffusion coefficient, that kind of diffusion coefficient, cathode thickness of this size, separator thickness of that size, so different parameters. And training the deep neural network can be seen here, validation loss. And now, testing the neural network projection. Okay, so these are two parameter sets that the network was not trained on. And what you can see is the simulation, the long and accurate simulation gives the same result as the deep neural network, the so-called multi-layer perceptron. Okay, it's extremely accurate, down to 0.0001. Okay, and there's a website to simulate it, and I can show it. It's basically very similar. It's just a little bit more complex model. Okay, so now diffusion coefficient in the cathode, cathode lithium intercalation rate, and you can see that I can change it, and it changes the spectrum. Okay, so you can see that there are many very interesting processes that goes on. And what the whole point of this is that now we can use this model to get the real parameters. Okay, we don't need weeks for that. We can get it in milliseconds. And that's a huge deal, because now battery management systems can use this model to get the parameters, all of the parameters that are relevant, diffusion coefficients, solid electrolyte interface thickness, and many others. Okay, and in the last minute of my talk, I would like to talk about something else. And it's the use of this complex impedance as a transfer function. So in analytical chemistry field, we use the complex impedance just as a quality assurance tool, or maybe an analytical tool. So we look at it and we say that, okay, this curve looks good, okay, maybe the SEI layer is too thick, so there are many parameters that we can get from it. But that's not the only thing we can use the complex impedance. We can use it as a transfer function which gets an input function, for example, something like this or this, and transfers it to the output function. What does it mean? We can now give this complex impedance the charging profile, so the currents that we are applying, and we can get back the potential profile. And that's my last slide I want to show. So the complex impedance is taken from 50% SOC, and it's here. So now you can see that I'm in real time changing the charging profile, and you can see that how the potential changes. So if I did this to a battery with this complex impedance, that would be the the potential that I would get. And it takes milliseconds to do that. And it's extremely accurate. Okay, so that's what I wanted to show here. And in conclusion, I just want to emphasize the last part. So changes in the structure properties of the electrochemical devices can be monitored in real time by non-invasive electrochemical experimental method coupled to simulations. Okay, so that's the take-home message here. Thank you very much.
Thank you.
Okay, so this model is a pseudo 2D model. That means that the particles are considered as a sphere. And these spheres cannot be too small, because if they are very, very small, then the SEI formation, the solid electrolyte layer formation, is accelerated. So we need to find a spot where SEI formation is not too large, and but the area is large enough that it's efficient. Okay, and it's around 5 to 20 micrometer particles. So that's the particle size that is simulated in this model. These are not really pores inside. So this is an intercalation process. So we have the graphene sheets. So it's graphite, basically, and the lithium can intercalate, can enter between these layers. There are no pores. It's really entering between the nanometer apart layers of the graphene. Yes. So it really can enter there.
Thank you very much. And thank you, Lajos.
You're welcome.
Thank you very much. Okay, before we start, just a short introduction. This would be more, let's say, material scientific. I hope that we'll start the presentation. I will talk to you about this type of new generation batteries, lithium sulfur battery, indeed. This should be maybe a new generation, new type. Thank you very much. Sorry. Anyway, okay, just that. No problem. So in the beginning of my talk, I would like to talk about the battery, so to say, roadmap. It means that I guess everybody uses nowadays lithium-ion batteries. These, as Lajos told, not just for the graphite, but also for the positive electrode materials. This is a lithium transition metal oxides, like nickel or cobalt-containing transition metal oxide. These are the generation 2, number 2, or 2A, 2B batteries. But of course, we know the limitations of those batteries. So the energy density, the power performance, power density performance, also the aging characteristics must be, or have to be, okay, it must be restarted. It must be, of course, enhanced. You have also maybe the user, the normal user for electric cars, the range problem. So you can drive a car with a 40, 60, 80 kilowatt hour battery cell, maybe 200, 300 kilometers, if the battery is fresh. Afterwards, you lose the range because of the battery aging. These are highly complicated and highly complex aging processes are occurring in the battery cell. And what we can do, But again, of course, not saying, okay, the lithium-ion batteries reached a limit, and we cannot enhance the performance of the lithium-ion batteries anymore, but we go for new chemistries, new cell designs, whatsoever. And this is what we hopefully you will see. Számítógépembe bekapcsoljuk esetleg? A saját gépemet betegyük ide. For instance, maybe you also heard about... Really?
Sorry.
So you maybe heard about the solid state batteries. When with the liquid electrolyte will be replaced. Okay, good. And will be replaced with a solid alternative. And this gives us maybe higher energy performance, more safety, intrinsic safety. Okay, this is the battery roadmap. So just to pick up here the rows and the most important information. This is the batteries what we are using currently. This generation 2. This should be, something is predicted or said. Okay, in 5 years or 2 years or whatsoever, the new chemistry will come. It will be always bit pushed to the near future. So maybe in 2025 we can use the silicon. Again, you could hear about that silicon is a really good and a nice electrode material because of the specific capacity, what we call in milliamp hour per gram. It's 10 times higher than that of the graphite. So instead of this 370, it should be almost 4,000 milliamp hour per gram. So it's a really prosperous material. The problem is the extreme volume change upon lithiation and delithiation, and that's why material scientists should design material which is capable to provide high capacity for a long term. Okay, so this is the generation 3, so-called advanced batteries, and hopefully in 2013, 14, 15, let's see, when Toyota wanted to have in the Olympic Games, the solid-state battery car. We still have the promise on solid-state batteries to enhance the energy density beyond 250 watt-hour per kilograms on a cell level into the range of 400, 500 watt-hour per kilogram. And then, of course, the generation 5 lithium air or lithium oxygen batteries, as in my opinion, still in the really, really fundamental scientific level, and they're still, in my, let's say, perception, it's still a primary cell, so it means it's not rechargeable. Maybe beyond or besides the solid state, so replacing here the liquid electrolyte, the organic electrolyte, which is dangerous, which is toxic, which is highly flammable, replacing the solid alternative, we can go for the so-called conversion type cathodes. So instead of this lithium intercalation electrodes, we can use conversion type, very interesting, very simple, everybody knows conversion type electrode from the lead acid battery, lead and lead oxide into lead sulfate. And this is what in this talk I would like to talk about the lithium sulfur. Okay, sorry. Why lithium sulfur? So this should be a new generation conversion type cathode for lithium-ion batteries. By the way, the same lithium shuttling principle, which is in the state-of-the-art batteries. The thing is, the point is that still the transition metal oxides, so the current batteries or the cathodes, have this kind of specific capacity. Sulfur, so elementary sulfur we are talking about, this yellow powder, everybody knows, more or less 10 times higher. It means from a cell level, from the 250, we could change, or we can enhance the energy density of this on cell level to 500. Please note that is 250. If you go for a car pack, it will be a maximum the half of it. So on a pack level in an electric car, you have on a system level 80 to 100 watt-hour per kilogram because of the structural materials found in the battery car pack. Advantages of the lithium sulfur: this is low cost, it's abundant, and the high theoretical capacity. Okay. The problem is associated with the sulfur cathode. Everything's really nice, it's cheap, it's high capacity, it's electrode, everything's fantastic. Yes and no. Because if we are playing around with the sulfur in the lithium-ion battery cell, okay, the anode, it's lithium metal, which is very typical for the new generation batteries. One should, and everybody want to use lithium metal anode in the in the anode side instead of graphite. The problem is, if the sulfur cathode we start to oxidize or start to, let's say, react with the lithium, then we have the so-called lithium polysulfides. There's Li2, S8, S6, etc. It's how the discharge or the process proceeds. And this is why, and many people call this cell, this is a liquid cathode cell, because in fact, sulfur and the discharge product, lithium sulfide, Li2S, it's not dissolving in the electrolyte, but all polysulfides here, long chain and short chain, it's dissolving in the liquid electrolyte. And we have a huge concentration difference across the separator. So you can imagine the anode side, which is basically you should not be any polysulfide. And then on the cathode side, we have the polysulfides dissolving the electrolyte. So we dissolve all sulfur content. And the concentration could be 6 to 8 molar concentration, really high concentration, depending on the sulfur loading and depending on the electrolyte filling, but we are talking about between 5 to 10 molar solvents. So it's a really high diffusion, let's say, concentration difference between the two side of the separator. And then this is how what we should, let's say, consider if we want to build the lithium sulfur battery. It is really good that we have a nice, secondly, just before I talk about the carbon content, sulfur is isolating. It's really this. Also, lithium-ion conductivity, electronic conductivity, it's basically negligible. We cannot say 10 to minus whatsoever. So that's why the sulfur should be incorporated into an electronic conductive host, a lightweight material, basically. And this is why we use always carbons, nanocarbons, graphite or graphene-based, carbon nanotubes, templated carbons, whatsoever. So this carbon network, first of all, it's electronic conductive matrix, so we can deliver the electrons, and of course in the pores, if you fill the electrolyte, the lithium ions can travel to the electrochemical sites, and then secondly, this highly porous carbon electronic conductive network also confines the sulfur, so it's the trapping. And of course, due to this polysulfide dissolution, one of the most important tasks, if it's dissolving, if we have the polysulfide, and if it's inside the electrolyte, then somehow suppress or make it, let's say, the velocity of the diffusion from the cathode side to the anode side across the electrolyte, somehow make it slower. So somehow trap the polysulfides. By the way, this is again polar, sulfur is non-polar. These polar molecules trap and somehow keep in the cathode side. So within the confine, within the pores of the carbon host. So this is what we call, first of all, if the tortuosity, if the porosity, it's well designed, then we call it as a kind of physical trapping. So the polysulfides will diffuse, they move, they want to travel, and of course, considering the concentration difference, they will definitely move, but fine-tuning, or let's say engineering the diffusion coefficient of the polysulfides, we can say, okay, if the diffusion, which is definitely takes place, takes longer time. Secondly, we have besides the physical anchoring or the physical confinement, we have also a tool, the so-called chemical confinement. And this is what Professor László showed us, the functional groups, the polar functional groups on the sulfur. These are hydrophilic domains on the carbon host, which can act as like molecular anchoring sites to kind of adsorption, let's say. They can adsorb and chemically anchor the polysulfides till they just decomposing into the final product lithium sulfide, Li2S, and they just, let's say, precipitating at the site. And what we did in our study, Okay, these are the major challenges. Maybe you can see later. This is what I said. Okay, these associated challenges with the lithium sulfur, these are the solutions. So first of all, we have to design a sulfur carbon nanocomposite, which basically has a twofold effect, no, threefold. First of all, electroconductive matrix. The carbon acts as an electroconductive matrix. Secondly, due to the optimum pore structure, we have this so-called physical confinement, and because of the surface chemistry of the carbon, we have the chemical confinement effect. How nowadays, let's say even it's not commercialized, but how, let's say, a state-of-the-art lithium sulfur battery cathode will be produced, time-consuming, you see, high energy consumption, in toxic solvents, melt diffusion or dissolution, and carbon disulfide and silly stuff. This is not good, so not that green and not that energy-saving method. What we did, instead of having this highly toxic and expensive solvents, we used in the department, there is a reactor, supercritical CO2. Supercritical CO2, I don't want to go afterwards deep into detail what is supercritical CO2. We consider at this moment and in this project as a good non-aprotic apolar solvent. We are working at 30, 32 Celsius or centigrade and 150 or 200 bars. So we have the solvent, a possible solvent for the sulfur. And also we are using a homemade or it's not commercial, but a reduced graphene oxide. This is made of graphite. So we chemically converted graphene. We are using as a sulfur host. And then you see basically combining the reduced graphene oxide with the supercritical CO2, basically what we wanted to have, it is a nice, homogeneous, in a sense of microstructure, a sulfur carbon nanocomposite, which afterwards incorporated the battery cell working properly, means we have high energy density and long cycle life. I talked about that reduced graphene oxide is basically this electronic conductive matrix. What we did, we have the reactor in the laboratory. We put the reagents, reduced graphene oxide and sulfur. We have a certain mass ratio between the two components. Let it treat, 150 bars to half day, and then this composite is recuperated from the reactor. Then we make so this is a really typical industrial process, a slurry-based process. We have the thin coating apparatus at the TTK, and then from this, from the electrode layer, this copper foil, it's about 80 microns, it's really thin metallic layer. We punch out electrodes, it is dried, and then it's very typical, we put together this CR2032, you know, this flat, somewhat bigger coin cell. These are our prototype cells. By the way, this process, everything is it's happening in the glove box, which is filled with argon, no humidity, no oxygen in the atmosphere. Good. These are some, we have not many time, so we have some basic material scientific or the material structural information before loading and after loading the sulfur. So we see that the sulfur is incorporated into the system. Some microscopy analysis, and based on this, we could say, and these are also, we published the results, so I think in the last stage we have in the review process, we just answered the referees' questions. What I want to show you, and this is, I think, maybe the last slide, if we have already 32 or 35. So we reached more or less 1,000 or above 1,000 milliamp hour per gram capacity. Again, for a lithium, NMC, LFP, or this kind of materials, we're talking about 160, 120. So this range is the order of magnitude. Most importantly, maybe, or more importantly, even after 200 charge discharge of full cycles 200 times, okay, for commercial cells, it's not that much. We have to target 1,000, 2,000 cycles, but nevertheless, for 200 cycles, we have a capacity retention of 82%, and per cycle, we have a very, let's say, acceptable decay rate. It means that after a prolonged cycling, even after 200 cycles, we could have well beyond or above 950, 960 milliamp hour per gram capacity. Even it is really very interesting. Okay, if you are talking about mobile applications, so like electric cars, power density, it's very important. So the energy can be stored and can be released in a fast charging. And even if 2C, 1C is 1 hour full charge discharge, 2C would be half an hour, and even the cell providing very much high capacity. Anyway, I just leave this slide here for further discussion, and I think I just ran out of time. Thank you very much for your attention.
Thank you very much. One question, comment. May I quickly ask, what is the sulfur content of this material?
It's 66%, so 1 to 2. The one part carbon and 2 part sulfur.
So it is fully incorporated in the material?
Should be, exactly, at least what the analysis said. Of course, the target, so the commercial grade cells containing 75% of sulfur. So it's, let's say, room for improvement.
After that, I think you moved to Freiburg for a while, and from Freiburg in the Breisgau. Yeah. Freiburg, and then you can move to Zurich. And he has many awards, many named lectures was given by him, but most importantly, he is honorary professor, or honorary doctor of our university since 2020, I think. So, and this is the first time, because of COVID, whatever, that he can give here a lecture. So, Hans-Jörg.
Yeah, thank you. Thank you very much. It's my pleasure to be here. And what I will present you today is indeed a collaborative work with the University of Budapest. So there is on this slide one name which I really would like to mention in particular, and that is Zoltan. So when Zoltan spent about 2.5 years in my laboratory, and we started actually this chemistry together, which I will use in order to entertain you a little bit at the end of this morning session. There is no applied chemistry in it. It's just pure synthetic, inorganic, molecular chemistry. And I hope that you find parts of it actually interesting. So when I started my career, I thought, what is actually a goal in synthetic chemistry is, especially if you work in specialty chemicals And you may know that phosphorus chemicals are widely used in industry as ligands, flame retardants. Actually, battery housings will need very fireproofed materials. Phosphorus is, for example, one of those. It's used as photoinitiators. So there are many, many applications. And if you look through the literature of how actually organophosphorus compounds are prepared, this is what I would say probably at this stage organic chemistry was in 200 years ago. So what mainly inorganic chemists do is we eliminate sodium chloride or we eliminate water, sometimes trimethylsilyl chloride, but inorganic chemistry still lacks sophisticated synthetic methods. And one of the main problems we have in inorganic chemistry is that in contrast to organic chemistry, we have no functional groups. There are no aldehydes, no carboxylic acids, there are no hydroxy groups. Everything we use in inorganic chemistry as a functional group actually needs to be prepared by a chemist, and very often these synthetic methods are not known. So we wanted to contribute to this area, which I think is a growing area of interest. Everything, even something which you produce in small amounts, needs to be produced in a highly efficient way, because we need to avoid waste. Waste is always a loss of energy. And one of the most simple functional groups in organophosphorus chemistry would be the Cp minus anion. It just contains one carbon, one phosphorus. You can use it as a nucleophile. You can perform cycloadditions to the triple bond. So this would really be a useful building block for organophosphorus compounds. The only problem is it's actually not known. And it's not growing on a tree, like, by the way, lithium neither. So there are a lot of materials which you apply and which we talk about, which actually need to be prepared in energy-consuming processes as well. So one of my ideas was, when I was a young man in your age, to make Cp minus, the true Cp minus. The problem is, how do you do this? And it took years and decades before an American postdoc who wanted to really to do some difficult chemistry in my laboratory actually succeeded in making a Cp minus ligand. And that, on this slide, I will not discuss this in detail, it's just something typical in inorganic chemistry. So we could make this compound. It actually was, even without us being asked to pay for it, it was on the cover page of the Angewandte Chemie. So we got some publicity from this. But in my whole career, this is the most useless compound I've ever prepared. You cannot do anything with this. It doesn't react with something, so it's very nice, and you need more than 100 atoms in order to stabilize the bond between two element centers. That is anything but atom efficient and atom economic. So that's not the right way in order to use the Cp as a synton and functional group in inorganic chemistry. So we actually thought we must make this much better. So we wanted to make sodium Cp. That was actually the original goal, like sodium cyanide. You would actually call this then sodium cyaphite. And then I have to admit, actually, this occurred after we discovered this. So we actually discovered then that already in 1894, American chemists tried to react sodium dihydrogen phosphide with carbon monoxide. You produce the desired sodium Cp and water. So a typical inorganic reaction where you eliminate water. The most interesting part actually is this sentence here. We have been obliged to discontinue this investigation for the present, but in the near future we shall take it up again. I discovered this 150 years later. So there was no continuation of that work, and what we learned from this is even in the 19th century, scientists had already problems of finding funding for fundamental research. So I'm pretty sure that because no money was paid, they actually could not continue this work. And that was exactly the time when Zoltan came into my laboratory, where we started to actually to find a way in order to repeat this experiment. And the first thing we needed to do was to find a reliable synthesis of sodium dihydrogen phosphide. And even if I'm talking about this today, I still find it fascinating that in inorganic chemistry with very few atoms, you can still find remarkable and surprising and unpredictable results. Because when we made sodium pH2, first of all, we make this from elemental sodium and elemental phosphorus at room temperature. That's already, you make a microcrystalline material at room temperature. That's already quite rare. And then we discovered that if you make the sodium dihydrogen phosphide in combination with sodium tertiary butoxide and you measure an NMR spectrum, you see two signals. Both of them are clearly pH2 minus. But how is this possible? So obviously sodium pH2 exists in two different forms in solution, and indeed what we detected is it's forming once a cluster with 13 sodium cations and one cluster with only 12 cations, and the exchange of the tertiary butoxide groups between these two cluster aggregates is so slow that you actually can see this separately on the NMR timescale. The good news is, for the first time, we had a reagent which was non-pyrophoric. You can dissolve it in organic solvents. You could indeed investigate the chemistry of sodium dihydrogen phosphide, a chemical which was actually known for decades before, but you couldn't really store it, nor you could really do chemistry with this. So we were then able to repeat this experiment, and we reacted sodium dihydrogen phosphide with carbon monoxide, like these American researchers in 1894, so about 120 years ago, before. And what we discovered is that it's not forming sodium CP, as was formulated. We are not losing water, which would be trivial. We actually lost hydrogen. So this is one of the rare reactions where you have an alpha elimination of dihydrogen, and we formed the phosphorus analog of cyanate, not of cyanide. But this compound here can now be made easily and on a different route. So we start in this case from phosphine, and we use methyl carbonate in the presence of a base in an organic solvent, and then within a couple of hours you can easily produce 200 grams of this material, the sodium phosphoenolate, as we call it, sodium OCP. And that is a new functional group. And at this exciting time, actually, Zoltan appeared. He did a lot of calculations on how this anion can actually be described theoretically. What kind of properties can we expect? And maybe the easiest way to express this is to look to these three resonance structures, of which two are trivial. So you can actually draw these two resonance structures. Each of them has a sizable weight to the electronic ground state. But maybe the most interesting one is actually this one, which is only participating with 7% to the electronic ground state, but which gives you the idea that OCP can actually be viewed as a carbon monoxide complex of P-. So we can eventually use the OCP as a P- transfer reagent. And that is, especially for inorganic chemists, maybe one of the most useful and exciting applications. And in order to cut a long story short, so most of this chemistry has actually been reviewed. I show you only one example where actually we did this. So when you react this iron 2 complex with sodium OCP, you can actually produce an iron phosphide cluster, which you cannot produce easily on another route. And what is interesting about this iron phosphide cluster is this is, for example, a material which you can use in order to electrochemically split water into hydrogen and dioxygen, and you can use actually this particular molecular catalyst for both the oxygen and the hydrogen evolution reaction. So that's one of the possibilities then. If you discover a new functional group, you find new ways in order to make new chemicals, eventually even useful ones, in a more efficient way. Another example, or another modification we then started to investigate is this one here. This is one rather recent result. So this was actually developed after Zoltán had been in my laboratory. And what we discovered is if you react this stanulated phosphaketene, so this is very simple to make, you take triphenyl tin chloride and sodium OCP, you can prepare and isolate this compound, and if you react this here with an amide, you actually eliminate this oxygen center and you substitute this for nitrogen. And what you have here is nothing else than the phosphorus analog of cyanamide. So material which you can easily make from nitrogen and carbon, calcium carbide. You can produce calcium cyanamide, and this would be the phosphorus analog of cyanamide. Oh, somebody already fell off the chair. And again, so this is another way of transforming this functional group. So instead of having the tin analog, we prepared also the silicon analog. And this one can also be described by 3 resonance structures, and there is one particular one. So in this case, we have a dianion instead of a monoanion. And what was inspiring here is actually that there are 2 forms where the phosphorus carries more than one lone pair, which in other words means these anion can eventually be used in order to make clusters where the phosphorus center bridges 2 or even more metal centers. And in which domain is that particularly interesting? Well, for late transition metal compounds. Late transition metal phosphides are actually unknown. And the dogma, to a certain extent, is, well, if you take an electron-rich element like phosphorus and you react this with an electron-rich transition metal, you will always have anti-bonding interaction between the lone pairs. So for that reason, you cannot use rhodium, for example, and heat this with elemental phosphorus in the hope to prepare rhodium phosphides as stable phases. So you need a molecular approach in order to do this. So rhodium phosphides are actually not known. And one example I can show you here is when we react this phosphorus analog of phosphocyanamide, we prepare again a cluster. In this case, however, we have 3 metal centers in a trigonal arrangement, and they are kept as we actually expected by the PCN2- anion. Again, this is a cluster which is new. It only carries olefins here at the metal center, which can be easily displaced. So the idea is to make these kind of rhodium phosphide clusters in a molecular way, then to support them on a support material and use them eventually as catalysts. However, of course, whenever you do something new, something unexpected will happen. So what we tried then here in this reaction is we used this cluster here, which I've shown you there, and we simply oxidized it. I mean, if this is electron-rich, a trivial reaction would be you oxidize it and you just withdraw electrons. And just as an example to show you how crazy chemistry is in some cases, if you oxidize this cluster, you lose cyanide. So you withdraw an electron, but you lose an anion. And the driving force for forming this cluster, I have no idea. I can only tell you this is formed here 90% yield. It's a completely new rhodium phosphide cluster, and the beauty is it carries really an open triangle composed from 3 rhodium centers, and we start to investigate the chemistry of these clusters, for example, in hydrogenation reactions. And that looks very promising. Another example, what if you discover a new functional group, how you can actually continue to develop and to find new functional groups, and with these new functional groups, new materials. That's also a reaction which was unexpected. So we again made this phosphaketene by reacting, in this case, a silyl chloride with NaOCP. This is actually something which Zoltán has investigated quite intensively, because it was surprising that this is the most stable isomer. The silicon does not bind to the oxygen, despite the fact that you would expect that silicon as an oxophilic element should actually bind to oxygen and not to phosphorus. So Zoltán could actually help us to understand why these phosphaketenes are thermodynamically more stable. So we can make this. Then we can react this with a nucleophilic carbene, which attacks here at the carbon center, and then something really remarkable happens. The carbon and the phosphorus exchange places. So we convert an anion with a PCO sequence in an anion with a CPO. So you flip around the carbon and the phosphorus. That's a quite unusual reaction. However, when we saw this, my idea was immediately, well, we simply need to add 2 electrons to this heterocumulene, then we will lose the carbene here and we use the siloxide as a leaving group, and that would be the ideal way of making CP-. So we did that reaction. Of course, this did not work as planned. We indeed lose siloxide, but we are not transferring 2 electrons. We actually eliminate siloxide and we produce a carbene CP radical, and that dimerizes. And that dimer then actually contains 2 carbon and 2 phosphorus centers, and to the 2 other carbons here are bound 2 carbene centers. The question is, what is this for a molecule? The first thing you do, of course, is then you crystallize it and you get the bond length data, and you can see the ring is absolutely planar. It's perfect, a perfectly planar 4-membered ring. The distance between the phosphorus centers is 2.7 angstrom. That's a little bit too long for a phosphorus-phosphorus bond, but still not long enough to exclude any kind of interaction between the phosphorus centers. So if you draw then resonance structures, you can actually draw a classical Lewis valence structure. However, if there would be really a bond between the phosphorus centers, what you would expect is that the 4-membered ring has a folded structure. So this classical Lewis structure is for sure one which has a very low weight to the electronic ground state. And in order to cut a long story short, this unusual C2P2 cycle is actually best described by a biradical structure into which this aromatic ring structure is mixed into about 40 to 50%. So this is a non-Kikuli molecule which contains a 4-membered C2P2 ring which has an aromatic 6-pi system. Rather unusual. If this is true, what you would expect is that you can use the C2P2 cycle in order to prepare complexes. And indeed, that works beautifully well. We can bind transition metal fragments, and in contrast to benzene complexes, these C2P2 metallic complexes are sometimes stable above 400 degrees centigrade, so much more stable than the corresponding arene complexes. And we are investigating these compounds as well. And then in my final part, I would like to talk a little bit about György Oláh. Oláh was, of course, as every one of you know, deeply interested in carbocations. And I will show you there is one example where we can use the C2P2 ring in order to solve a classical problem in carbocation chemistry. And in order to do so, we simply strived through some reactivities, and what we discovered very recently is that you can make the C2P2 cycle to react with germanium dichloride in the presence of an halide abstracting reagent. What you do in this reaction is you actually place a germanium 2+ above the C2P2 cycle. And you make this molecule, which, if you really look to this really looks crazy. I mean, this looks like a hat composed from 2 carbon and 2 phosphorus center, and then on top of it is a germanium. Remarkable, unusual. However, it's not so unusual. It's actually linked to a fundamental concept in inorganic chemistry, and these are clusters. If you apply the counting rules for weight-Mingos clusters, you quickly realize that this germanium C2P2 cluster is a classical Nido weight-Mingos cluster. And as such, if you perform some isovalence electronic substitutions, the C2P2 germanium cluster is linked to pyrimidine, which is until today an elusive molecule and could not be prepared. And then when I was in your age, there was a lecture given by Raguel von Schleyer, who was a good friend of György Oláh. So they did really a lot of work together on carbocations. And I was fascinated by a lecture of Raguel von Schleyer, where he actually explained to us as students that if you would oxidize cyclopentadienide, so you remove 2 electrons and you would oxidize cyclopentadienide to form C5H5+, which as a cycle would be anti-aromatic. This anti-aromatic cycle would rearrange in order to form a nido cluster. And if you really think about this, that's a dramatic structural change. You take a 3D dimensional object, you add 1 electron pair, and you flatten this out and form an aromatic cycle. And how does that process actually proceed? So when we made this germanium compound, which is isovalence electronic to this pyrimidine, I immediately remembered, well, maybe this pyrimidine could help us to understand how such a process might actually work. And this is shown in a schematic way here. So if you take a closo cluster, for example, and you would add 2 electrons, you have 2 chances. You can either convert this into a nido cluster, or you can convert this into an anti-aromatic cycle. If you then, based on stability reasons, you would always expect it's actually forming the nido cluster. If you then add the nido cluster, take the nido cluster, you add 2 electrons, you have again 2 choices. Either you form an arachnocluster or you form an aromatic cycle. And in order to study such a structural transformation, it actually seemed to us most likely that if you take a nido cluster and you add 2 electrons, you will convert this into a planar cycle and vice versa. So that's a profound structural change triggered by 2 electrons. The first question is, of course, how does such a reaction actually proceed? There is no, I mean, we just heard a lot about electrochemistry. To my knowledge, there is no chemical process where 2 electrons are simultaneously transferred. You always add 1 electron after the other. So if such a process occurs, there must be a huge world of 1 electron reduced and products in between the cluster and the cycle. So we wanted to discover this. So first thing you do is then you take this cluster, you add electrons, and you simply investigate this by cyclic voltammetry. And luckily for us, this is a very simple process because we observe 2 reversible 1 electron redox waves. So from that experiment, we already know this reduction of this dicationic cluster proceeds stepwise in 1 electron steps. And since the potential difference between the first and the second reduction is sufficiently large, the disproportionation constant of the mono-reduced compound is small, you can actually isolate the intermediate. And that is what my coworker Peter Kuborger did. So we could crystallize the mono-reduced compound, so the radical cation, which is interesting because what you see is when you add 1 electron to the dicationic cluster, you open already 1 of the cluster edges. That's exactly what you expect from cluster chemistry. But in this case, it already occurred when you add 1 electron. This compound is by itself quite interesting because you can describe this with 2 resonance forms, which both of them are dystonic radicals. So the charge and the radical center are not located on the same atom center. So theoretically, this is already by itself an interesting species. And then you can reduce this further. So you can take the dication, you add 2 electrons. We can see an intermediate. This one we cannot isolate. And that indeed rearranges in a slow reaction to form a planar cycle. So this original idea von Raguis-Schleyer is really working. You can take a cluster, you add 2 electrons, and you convert the cluster into a planar cycle. Well, since we could isolate the radical cation, we could also investigate a little bit its chemistry, and what we discovered is that this compound is not stable either. It also rearranges very slowly and forms a cycle, a compound with a cyclic structure. However, in this case, a dimer actually is obtained. So this cluster likely rearranges into a radical cation with a planar structure and that dimerizes in order to form this dimer, which is again stable. And as you will see in a second, this is a key intermediate for the understanding of how this process actually really works. So you can take then this dimeric dication, again reduce it with electrons, and sure enough you cleave the germanium-germanium bond and you form the aromatic 6-pi flat cycle. And that is, again, as you can see, isolated, crystallized, so we know the structure, and we can actually work with this material and investigate its chemistry. And that's exactly the next step which we did. So, what did we learn so far? The reduction of the dication proceeds stepwise. We form a radical cation as an intermediate, which slowly rearranges into a planar cycle, but probably, at least in a chemical reaction, is reduced a second time in a fast electrochemical, in a fast chemical reduction reaction, and then forms this intermediate, which have not isolated but observed, and this rearranges into the planar cycle. So that is the reduction reaction. Of course, we would like to do this, investigate the inverse reaction, the oxidation of the planar cycle as well, and that's a little bit more complicated, and since I'm running out of time and you are hungry, I will very rapidly actually get you through this, and you have simply to believe me that we understand this process very well. So first of all, this dication can interestingly be reversibly oxidized to give the trication, and the trication is irreversibly reduced in order to form the tetracation. We can also take this dication, bicyclic dication, and reduce it, and then we form a very unstable intermediate. So this compound is not observed, not even observed, despite then isolated. This one actually disproportionates to give the neutral ring and the dication. So that is then, and then this neutral cycle is then oxidized. So if you look to the cyclic voltammogram, this is actually then reflected here in irreversible reduction wave. This is this process. We form this cycle, and this cycle is then irreversibly oxidized in the oxidative scan. If we start from the cycle and we oxidize it, we also form this unstable radical dication with a bicyclic structure. And in this case, this compound again disproportionates. So when we start from the cycle and we oxidize it, so we start with an oxidative scan, we see exactly the same cyclic voltammogram than for the bicyclic dication, only with inverse current intensities. And that is the proof that this compound here is in both processes the unstable intermediate. And that allows us then to complete the picture. When we start from the dication, we reduce it stepwise in 2 electrons to form this neutral intermediate, which then rearranges slowly to form this cycle. When we have the cycle, we can oxidize it to give this very unstable short-lived intermediate, which either dimerizes to give this dication, or it intercepts a non-oxidized cycle to give this unstable intermediate. And both this compound and this compound are then reversibly oxidized to give the trication, and the trication is irreversibly oxidized to give the tetracation, which then rearranges back into the cluster. So we have fully understood now this process. And the interesting thing is actually the reduction proceeds on a different pathway than the oxidation. But in principle, you can actually really reverse the process. So you can reduce a cluster to form a planar cycle and oxidize the planar cycle to form back a cluster. If we would succeed in lowering the activation barriers for this process, then in principle, you can dream about a material where you take 2 electrons in a stepwise manner, and then you change the structure from a cluster to a cycle, and then when you remove the electrons, you change back the cycle to the cluster. And that's exactly what you would like to see in smart materials. So if we would succeed in finding a cluster compound where we could actually, in a fast reaction, add 2 electrons, convert this to a cycle, and then reoxidize the cycle, you can actually then dramatically change the physical properties of such a material. In this particular case, which I've shown you here, it would mean, for example, that the cluster has a very small dipole moment, which is perpendicular to the basal C2P2 plane. If you would convert this on the surface into the planar compound, we actually would generate a molecule with a sizable dipole moment, and the dipole moment is flipped by 90 degrees. And if we reverse this process, you could, for example, use this in principle in order to modify or modulate infrared radiation. That's a long time to go. I will probably not experience this. So it actually brings me to the epilogue, what happened to the CP-, which I wanted to make. Fortunately, a very good friend of ours, of Zoltan and me, Jose Goicoechea, recently could actually make CP-. It has to be noted, however, that even in this case, so this is a much better CP- transfer reagent as shown in this reaction here, but still you need about 75 atoms in order to make the CP-. So the true challenge to make sodium CP- is still out. So maybe some of you can actually do this. You know, that's still not atom economic. It's much better than what we did with our ruthenium complex, but it's still not the holy grail in organophosphorus chemistry. So my trivial take-home messages. I think the most important message is, especially to young scientists, if you think you have a great idea, you can be sure that somebody else had it before. So what does that mean? Look carefully into the literature. So as we discovered, sodium CP- was not our idea. People had this 120 years before. Solutions to a problem come mostly unexpected. So as I hoped I could show you this intriguing problem which was presented to me as a student of how you can actually link the world of clusters into the world of aromatic cycles simply by adding electron pairs, which is already a fundamentally interesting problem, can be dissolved eventually with a cluster you never thought that these kind of molecules eventually may exist. So pyramidane is elusive and likely will remain elusive as a stable molecule. If you make heteroatom analogs of these compounds, they might actually be very stable. And then finally, because I have to read this more and more often when I submit my papers, that this chemistry which I'm doing is so useless and exotic. I simply wish to remind you that even our first speaker talking about carbon nitride, this was 1877 that Wöhler discovered carbon nitride by simply heating melanin. And then this material was forgotten, and now all of a sudden it's probably the material of the 21st century. So you never know when an experimental or scientific result becomes important or not, which is, I think, still for you a good driving or motivation in order to do also experimental chemistry, because as a chemist, you are the only scientist who can make in this universe new materials. A physicist cannot do this, and a biologist cannot do this either. But you, as a chemist, you can do it. Thank you very much for your attention.
Interesting talk, as usual. Questions or comments?
No. Thank you very much for the talk. My question would be about this cluster and cycle structure. How many times can you cycle it? So is there any degradation? I know this is application, so if we really want to apply this in the long run, it has to survive thousands or millions of
Yeah, I mean, of course, since the process takes time, 2 days in order to make the rearrangement, my students have no time to recycle. But we did this actually 3 times, which is for any kind of application, of course, absolutely useless. But in principle, I had no time. But if you would change the substituents a little bit, that has a dramatic influence on the barriers. But it's a complicated process. But in principle, of course, if you would really arrange these kind of molecules on a surface and they would be isolated, I mean, you add 2 electrons, you have a rearrangement. You remove 2 electrons, you have another rearrangement. In principle, this must be eternally, because you have no bimolecular reactions. You just add electrons and you remove electrons. And that's actually what I find so fascinating in this process. it's a little bit like sulfur. I mean, sulfur is also one of these few rare molecules. So one of the previous speakers talked about the reduction of sulfur. But if you oxidize sulfur, you form a sulfur-sulfur bond in the S8 ring. And that can be cycled millions of times as long as you keep the sulfur molecules insulated. As soon as you allow bimolecular reactions, you will always get some side reactions and then eventually degradation.
Any other questions or comments? Well, you had this germanium story. When you get the 5-membered ring, it is basically a germylane.
Yes. Germolite. I think diphosphorgermolite would be the UPAC nomenclature.
Maybe. You do not expect to make the carbene in a similar way. You mentioned it already, and I agree that it should be more difficult. But what about the silylane?
Yeah, that is I knew that this question will come. So we can make the tin compound, that is easy. So we can make the analogous tin compound, and I think we have a very, very, very bad crystal structure. But since last week, we have probably also the silicon analog. But as long as I'm not 100% sure about the composition, I prefer not. But I think this can be made. But it's much more unstable than the germanium compound. Yeah. As usual. I mean, even the tin compound is actually unstable. Bizarrely, it loses elemental tin. So if you make the tin compound and you heat this, actually you produce tin, which of course maybe for an application can be interesting because you can use then these C2P molecules as transporters for tin atoms. But I mean, we will not investigate this. And the silicon compound, we have the impression, actually inserts indeed into CH bonds. So it may undergo oxidative addition reactions.
I see no other questions.
Yeah, thank you very much. Yeah, it was my pleasure to be here. Just pray the next time that the sun is out. I was actually expecting that Budapest will be sizzling hot. And I was looking forward to some warm summer days, and unfortunately this is not the case. We talked already about this yesterday, but so you should actually try to have an influence on the weather.